So in today's class, we are going to understand, revisit, learn kinematics of rotation, where we will learn about angular displacement, angular velocity and angular acceleration, relation between angular and linear quantities, etc. I hope you can hear me clearly and see this feed cleanly. So, when we talk about rotation of bodies, we are actually looking at a class of bodies which is called as a rigid body. Now, what are rigid bodies? The rigid bodies are bodies which don't deform when forces are applied on it. So, normally, if you look into your day to day life, you will find that howsoever tough a body is, eventually you can apply some force on it by which you can deform it. So really in practice, we don't have real rigid bodies. But in our approximation, we can ignore these deformations and we will assume that the bodies are rigid. So that's the whole idea we are going to carry forward in our discussion. That a rigid body is one which doesn't deform, and this is a partial approximation, or we are, as we have already explained in the beginning, physics believes in model building. So we will make a model of a rigid body where we will assume that the bodies don't deform when forces are applied on it. Such models are called idealized models, and we are sticking to it for the time being. Now, whenever bodies rotate, there will always be some set of points which don't move, or around those points, the body is can be seen to be moving in concentric circles. All the particles of the bodies will move around that locus of points in concentric circles. Locus of such point is called as axis of rotation. It's a straight line and it may or may not pass through the body. So example, blades of the fan revolves around an axis passing through its center. So suppose if I have a fan here, these are the blades. Now when the fan rotates like this, then you will find that any point if you take, suppose you take a point here, it will move in circle. If you take a point here, it will move in larger circle. If you take a point at the periphery, it will move in the biggest circle. All these points, you can see that they are moving around some center point here. So although other points who are lying on this center, they form a locus of all such points will form a straight line. And such a straight line is called as axis. So axis is a locus of points about which the particles of a rotating rigid bodies revolve in concentric circles. So like this, they keep revolving. Axis of rotation is very important. It will be there everywhere. For example, if you open or close the door, that is another example of rotation. The axis of rotation passes through the hinges of the door. If you open or close the tap, then the axis of rotation passes through the center of the tap, etc. It can pass through a body, it may not pass through a body. So for example, if a ring is revolving, if you have a ring shaped, a wire bent in the form of a ring, or maybe a bangle or something like that, and if it's spinning about its natural axis, then the axis is not the part of the body. For example, when earth revolves around sun, the axis passes through the sun and not pass through the earth. So the axis can go through the body or it may not go through the body. So we have to remember that. Now, rotation can be classified depending on whether the axis is fixed or it is moving. So we are right now, we will in the beginning part of this topic, we are going to focus on fixed axis rotation. The axis of rotation of a rotating body is at rest in the frame of reference in which the observations are being made, and it does not change its direction in that frame. Then it is called a fixed axis rotation. So remember that there are two things. The axis of rotation should not move and it should also not change its direction. So all the particles here, they move in pure circle, pure concentric circles. Also, it is also referred as pure rotation, fixed axis rotations. I mean, pure rotation is not a very, uh, when you say pure rotation, it means the path followed by all the particles are defined concentric circles. The trajectory of all the particles of the body are circles. So example, a motor shaft. So you know big motors which are used in industries. When their shafts rotate, the motors are normally placed on very strong rigid supports and they don't move. So when the shaft rotates, it rotates about its fixed axis. Even a merry-go-round, I'll show you an example. A giant wheel in the carnivals, their axis is horizontal. Here I have one example of fixed axis rotation. So this child is sitting on a merry-go-round kind of situation and revolving. You can see that it is a fixed axis rotation. Where is the axis of rotation? The axis of rotation passes through the center and it's vertical. So somewhere here at the center and it's vertical is the axis of rotation. It is fixed. It is not moving. Remember that. All the points, uh, any point if you take on these chairs or anywhere else which are rotating, they are moving in circles about that axis of rotation. So this is an example of fixed axis rotation. There can be moving axis rotations. If the axis of rotation of a rotating body is moving in some reference frame and or changing its direction in that frame, then it is called as moving axis rotation. So moving axis rotations are more complicated. Here all the particles do not move in trajectories which are concentric circles. So remember the particle will still move about the axis in the form of circular manner. But since the axis itself is moving, the trajectory of each particle will not be a circle. The example is a spinning top, a rolling wheel, of a vehicle, a gyroscope, etc. So I will show you one example. You can see that here a body is rolling downward. So as the body is rolling downward, its axis of rotation passes through its center and it's perpendicular to the plane of the body. But the axis of rotation is not fixed. It keeps moving in the downward direction. So it comes in this category where the axis of rotation is moving in the reference frame. Example, if you all must have seen spinning of a top. So when a top spins, you know that its axis wobbles, or even the Earth's axis of rotation in the space wobbles. So these are all the examples of moving axis rotation. Now, in this chapter or in this topic of rotation, we are going to first focus only on fixed axis rotation. Rotation is a big topic. There are a lot of subtopics. So for next few lectures, we are going to focus only on fixed axis rotations. And once the moving axis rotations begin, we will check that. So let's check quickly the kinematics of rotation. That's actually the central theme of this lecture. So we first define angular displacement. So when a rigid body rotates, then position vector of any point, suppose if this represents the rotation of a rigid body, then any point P, position will keep changing in an angular manner about the axis. Axis passes through the point O. So I can always draw a reference x-axis, and with respect to reference x-axis, I can measure the angle by which the position vector representing point P rotates. This angle I can call as theta, sometimes delta theta, and this will be called as angular displacement. It is the angle traced by position vector of a point from a fixed axis. This is my fixed axis. Remember, this is very important. You have to decide your one axis as your fixed axis. You can give it any name. In my case, I call it as x-axis. So it's the angle traced by position vector of a point from a fixed axis as it moves on a circular path in pure rotation. So this is a circular path on which the particle is going. This is the position vector and it makes an angle theta. Now we have some nomenclature over it, or some traditional way of handling its direction. Angle is positive if it is measured anti-clockwise. Remember, this is the tradition we will carry all along. It can be one of the two, either positive or negative. We have selected positive. Anti-clockwise. So I hope everyone knows how to watch a time in the clock, how the clock hands move. So if the body is moving in a sense which is opposite to it, then the angle theta is positive, or increasing angle theta, we say that. Angle is negative if it is measured clockwise. So if it is moving, say, in clockwise sense, then the angle is negative. Now, whether it's a scalar or a vector, so when the angular displacement is finite, then it is a scalar quantity. When it is infinitesimally small, then it is a vector quantity. Now that may seem to you very odd. Same quantity, sometimes it's a scalar, sometimes it's vector, but that is true. finite angular displacement, when it is finite, it does not obey the law of vector addition. That is why we keep it in the category of scalar quantity. But when it is infinitesimally small, as the angular displacement becomes smaller and smaller, it starts obeying the law of vector addition, and therefore it goes in the category of vector quantities. You can elaborate on this further on by yourself. What is angular so let's see the direction, or let's see the measure of angular displacement. So we suppose if the radius vector is here at some time and then it goes here after some time, it traces out an angle theta, and on the circle an arc is created. Arc length is s. So now in this case, we can define angular displacement theta as the ratio of arc length upon radius, that is s upon r. So you can see that, and this is measured in radians. You can see that this is a dimensionless quantity. S upon R does not have a dimension, but it has a unit. It is measured in radians. That's SI unit. 1 radian, as we are all familiar, is 360 degrees upon 2 pi. So 360 degree, we say when it completes the circle. 2 pi is the radian measure, which is 57.3 degrees. So remember this figure. This becomes very handy later on. 1 radian is approximately 57.3 degrees, or 180 degree is nothing but pi radian. 90 degree is nothing but pi by 2 radian. Most of these nomenclature you are already familiar, so just a revision. But go ahead. Let's go ahead. How do we define angular velocity? Anybody? So, angular velocity is rate of change of angular displacement. So, it is the time rate of change of angular displacement. It is called angular velocity. So let's say a point is here at time t1. Its radius vector makes an angle theta 1 with the x-axis. After time delta t, that is at time t2, the particle reaches here, so that its radius vector is now making an angle theta 2 with the positive x-axis. So the change in the angular displacement is delta theta, which is theta 2 minus theta 1. Direction of rotation is taken anti-clockwise. So change in theta, delta theta is theta 2 minus theta 1. Change in time is delta t. Therefore, I can define my angular velocity as omega average z is equal to theta 2 minus theta 1 upon t2 minus t1. Theta 2 minus theta 1 is delta theta. T2 minus t1 is delta t. So this is called as average angular velocity. I'm writing z here because omega is directed in the direction of z-axis in this diagram. The rotation is happening in xy plane. This is x-axis, this is y-axis. Rotation is happening in xy plane. I will show you in a very short while how omega is in Z plane or towards the Z direction. But before that, average omega is delta theta by delta t. The instantaneous angular velocity is given by taking the limit of delta t to 0. So as the delta t tends to 0, omega z is limit of delta t tending to 0, delta theta by delta t, which is nothing but d theta by dt. So if you have a rigid body, then all the points of the rigid body, all the parts of the rotating rigid body has the same angular velocity. So we have to remember this. We are going to use this fact. So if the angular velocity of one point is given, then the angular velocity of all the points are going to be same if it's a rotating rigid body. So please remember that. What are the units of angular velocity? So it's angle divided by time. So it's revolutions per second, or in SI units it is called as radian per second. If it makes one revolution, then it covers an angle of 2 pi radian. So it's one revolution per second is nothing but 2 pi radian per second, where unit is radian per second. One revolution per minute is 2 pi by 60 radian per second. Do remember that 1 radian per second is approximately 10 rpm, or 10 rpm is 1 radian per second. This will be very handy when we solve the problems. Direction of rotation. What will be the direction of angular velocity? So the angular velocity is positive if the body is rotating in the direction of increasing theta, that is counterclockwise. So if it is moving in an anti-clockwise sense, we say omega as positive. If it is moving in clockwise sense, then we take omega as negative. So I have here illustration given in the diagrams. So if it is moving in an anti-clockwise sense, then omega is positive. The direction of omega can be given by the right hand rule. So you take your right hand out, you curl the right hand fingers in the direction of rotation like this. Then the outstretched thumb gives me the direction of omega. So if it is omega is greater than 0 or positive, that means if omega is if rotation is anti-clockwise, omega is considered positive. If omega is clockwise like this, rotation is clockwise, omega is assumed to be less than 0 or negative. Then if you curl your fingers in the direction of rotation, then your right hand thumb will go in the downward direction. So the direction will reverse. You can see that the plane of the body or the plane of rotation is 1 this way, and omega is now we are pointing in this way. So the omega points always perpendicular to the plane of rotation. So there are two planes of rotation, one is upward, one is downward. So depending on which way it rotates, that way omega points. So being positive or negative takes care of both the ways of rotation, either upward, either omega positive or omega negative. Now, can you look at if you are at your home, can you look at your ceiling fan and tell me the direction of omega for it? Is it positive or is it negative? You can text your answers. Check the ceiling fan at your home. Then you can point how, look at its direction of rotation, and take your right hand out. Curl the fingers in the direction of rotation of the ceiling fan. Take the thumb out. Tell me whether the omega is positive or it is negative. Savio says it's negative. So you have to really see how it rotates. So at least fan at my home, if I look at it, it goes in an anti-clockwise sense. So if I curl the curl my fingers in the direction of rotations of the blades of the fan, and it points downward. The rotation of the fan for me is anti-clockwise as far as I can see. So I will take it as positive. So that's the judgment that you have to make. Anytime if a body is rotating and if you want to ascertain the direction, follow this principle. Don't forget that you have to use the right hand. If you by chance use the left hand, then you will be incorrect. Let's go to the angular acceleration. The rate of change in the angular velocity is angular acceleration. So let's say that the body is rotating at time t1 with angular velocity omega 1, and at time t2 angular velocity omega 2. The z is taken because in our diagrams we are showing omega along the z axis, body is rotating in xy plane. For the time being we can ignore it. So as time changes, omega changes, and therefore average angular acceleration is given by omega 2 minus omega 1 upon t2 minus t1, which is delta omega upon delta t. Instantaneous angular acceleration is given by taking limit of delta t to 0. So as the limit of delta t tends to 0, delta omega by delta t will become d omega by dt, or derivative of omega with respect to t or time. Is so omega can be written as d theta by dt. So alpha, which is angular acceleration, can be written as second order derivative of theta, that is d2 theta by dt square. Again, as usual in angular, as it was in angular velocity, at any instant every part of a rotating rigid body has the same angular acceleration. So it's not that a particle which is close to the axis will have different angular acceleration. No, all the particles will have same angular acceleration. What will be the unit of angular acceleration? So the unit of angular acceleration can be defined omega's unit divided by time. So it will be radian. Omega is radian per second already, divided by 1 more second. So it is radian per second square. Do remember that. How do we sense the direction of angular acceleration? So that's a straightforward. We can recall the direction of linear acceleration along a straight line. So if you remember, in a straight line motion, if the linear velocity is increasing, that means acceleration is in the same direction as that of linear velocity. If the linear velocity is decreasing, that means the acceleration is in opposite direction of that of linear velocity. So we can put the same terminology here also. If omega is increasing, then alpha has the same direction as omega. So if the angular speed is increasing, if the angular if omega is decreasing, if omega is increasing, then alpha has the same direction as omega. If omega is decreasing, then alpha is opposite direction as omega. So here I have two examples. If my omega values are increasing, then alpha and omega point in the same direction. If my omega values are decreasing, then omega and alpha points in a direction opposite to it. So again, the fan is a wonderful example. When you put the fan on from a uh, turned off state, if you put the fan on, then the angular velocity increases, then its alpha and omega points in the same direction. When you turn the fan off, the angular velocity decreases, so alpha now points in the opposite direction. Yes, Gayatri. Santosh, your question is very genuine, whether it is with respect to ceiling or not. Gayatri, your answer is also correct. Uh, Most of the time when you are assessing the rotation, you are the observer, so you have to do it with respect to you, unless there is a reference frame given. So if you say the reference frame is ceiling, then the description changes. I did ask you, how do you perceive the direction of rotation? So thank you to both of you. So let me quickly go to the kinematical equations for rotation. We know the kinematical equations for straight line motion. So we have just defined alpha as omega 2 minus omega 1 upon T2 minus T1. So I will say my T1 as 0 and omega 1 as omega 0. That is when the observations began, my angular velocity was omega 0. I would call it as initial angular velocity. And at time t, my angular velocity is omega, which I would call as final angular velocity. Therefore, alpha is omega minus omega 0 upon t minus t0. I can quickly rearrange the term and I will get omega is equal to alpha t omega 0 plus alpha t. So omega is equal to omega 0 plus alpha t. This is my first kinematical equation for rotation. You might recall a similar kinematical equation in linear motion. V is equal to u plus at. So do remember there are parallels, and we will check that as well. Average omega if alpha is constant. Remember, we are deriving these equations for the cases when alpha is constant. If alpha is changing, then these equations will not hold. So if alpha is constant, then average angular velocity can be given as sum of initial and final angular velocities divided by 2. Okay, but average angular velocity is given by theta minus theta 0 upon t minus t0 as well, displacement upon time. So I can equate these two equations, and if I equate these two equations, I can derive an equation for theta minus theta 0, that is angular displacement. So angular displacement is omega 0 t plus half alpha t square. So if you remember, the parallel it has with the linear motion is S is equal to ut plus half at square. So that is my second kinematical equation. Now I can take this first equation and write it in terms of time. So time is equal to omega minus omega 0 upon alpha. Okay, and then use this time equation in equation 2. So place this here and place this here. So you eliminate time altogether from your discussion, and you are left with only theta, theta 0, omega, omega 0 and alpha. So when you solve it, you get your third kinematical equation. Final angular velocity omega square is equal to omega 0 square plus 2 alpha theta minus theta 0. Find omega square is equal to omega 0 square plus 2 alpha theta minus theta 0. So this is in parallel with the third kinematical equation. V square is equal to u square plus 2as. Remember, I'm not writing displacement just as theta, but I'm writing it as theta minus theta 0, because sometimes the initial rotation value may not, initial angular displacement may not be 0. So if the initial angular displacement is 0, this term will vanish, otherwise not. So be careful. So in fact, I have written 3 kinematical equations, but sometimes we refer 4 kinematical equations. This also is one of the important equation. Omega average is omega plus omega 0 by 2. So I hope that is clear to everyone. So here my parallels, I am drawing the 2 parallels. A is in linear motion, A is constant. Here alpha is constant. We write V is equal to V0 plus AT. Here we write omega is equal to omega 0 plus alpha t. So you can see that your initial velocity is replaced by final velocity. V is replaced by omega. A is replaced by alpha. So you don't have to remember a new equation. So very straightforward parallels. X minus x0 here, theta minus theta 0 here. So I have already discussed these. So let's go further. That perhaps could be the last topic. Relation between linear and rotational quantities. So we have already seen in the beginning that theta is arc length upon radius. So obviously my arc length is radius into theta. Now I can take derivative of this equation both sides with respect to time. So I'll make it ds by dt. So when I make it ds by dt, it is equal to r times d theta by dt. R is a constant here, so it will come out of the derivative. So ds by dt is equal to r times d theta by dt. But what is ds by dt? ds by dt is nothing but the linear velocity. Okay. So ds by dt is nothing but linear velocity, and d theta by dt, it is nothing but the angular velocity. So this equation is a very important equation. It relates linear velocity with the angular velocity. V is equal to r omega. Okay, so I hope you all can get this. Many of you might be familiar already with this equation. If you are not, look at these simple steps. These are very self-explanatory. How do I get my acceleration? So I take derivative of this equation. The derivative of this equation will give me an acceleration which is, we call it as tangential acceleration. So dv by dt, r is again constant, so it will become r d omega by dt. D omega by dt is nothing but alpha. So dv by dt, which is a tan or a tangential, can be written as r alpha. So here is the situation in my diagram. This is the rotational or circular motion path. Particle is moving, the rigid body is performing a rotation, it is in the background. A particle P of the rigid body is moving in the circle. Now this acceleration, tangential acceleration, is the rate of change of the magnitude of the velocity. That is the rate of change of the speed. Velocity works tangential, and therefore this acceleration works tangential. Now in this diagram I'm showing a tan having the same direction as v. So if acceleration has the same direction as v, then the speed will increase. The speed of the particle will go on increasing. If the speed is, if a tan is pointing in the other way, suppose a tangential is anti-parallel to v vector pointing this way, a tangential pointing in this direction. In that case, the acceleration is opposite to velocity and speed will go on decreasing. So in both cases, acceleration is tangential to the path of the particle, that is the circular path. So we call it tangential acceleration, and its function is to increase or decrease, that is to change the magnitude of the velocity, that is the speed of the body. So it changes the magnitude of the particle's velocity, that is its speed. What happens to the direction of the particle's velocity? So we know that the direction also changes. We have already learned in Newton's laws of motion that the acceleration responsible for that change is called radial acceleration, which is given by v square by r or omega square r. It acts radially inward. It is also called as centripetal, and it changes the direction of velocity. So I have two accelerations. One is tangential and one is towards the center. The net acceleration of the particle is given by the vector sum of these two. So this is the net acceleration, A, vector A. It is pointing in this direction. So if the speed is increasing, it will point in this direction. If the speed is decreasing, it will point in the opposite direction. So, okay, we stop here. Thank you.